All right, now in this video I'm going to be showing you how to solve a much more complicated Q equals MC delta T kind of an equation. And because it's talking about the energy flow between two different components in this experiment, if you will. This is actually what we're going to be doing in lab when I return from being away. So let's take a look and see and break it down into pieces so it's a little easier to see what's happening. A 400-gram piece of iron is heated in a flame. It's then dropped into a beaker of 1,000 grams of water that's at 20 degrees Celsius. So you can imagine what's happening. You have a Bunsen burner. You hold this 400-gram piece of iron into the flame. You hold it there for a while so that it all gets hot. And then you drop it into the water. What's going to happen to the temperature of the water? It's going to increase dramatically because you're taking this really hot piece of iron and you're putting it into the water. So the water is going to get hotter, the iron is going to get colder. So I already want you thinking about this energy flow. The final temperature of both the water and the iron is 32.8 degrees Celsius because again, the energy flows. The hot iron gets dropped into the water heats up as the iron loses its energy to the water. So the iron is going to get colder, the water is going to get hotter. So what was the temperature of the iron just before it was dropped into the water? So this is a tough problem. We have to break it down into our pieces. So the first thing that is really important is the iron is losing energy. It's going to get colder. So the negative Q of the iron is equal to the positive Q of the water. We're assuming that all of the energy from the iron goes into the water, the surroundings. Okay, so now you can see we have two sides of this equation. We need to figure out what's happening with the iron on one side, what's happening with the water on the other side, and then eventually we're going to set them equal in magnitude, but opposite in sign to each other. So over here we're going to figure out what's happening with the iron. So MC delta T. So the mass of the iron is 400 grams. The specific heat capacity of the iron, I didn't write it in here, but the specific heat capacity of iron is 0.45 joules per gram degree Celsius or gram Kelvin. The delta T is going to be T final minus T initial. The final temperature of the iron is 32.8 degrees Celsius. The initial temperature of the iron is what we're solving for. Let's go over here and talk about what's going on with the water. So Q equals MC delta T. M is equal to 1,000 grams because we have 1,000 grams of the water. The specific heat capacity of the water, again, I didn't write it down. This is one that you're going to have memorized by the end of this, is 4.184 joules per gram degree Celsius or gram Kelvin. As I explained in the last video when you're talking about a delta, delta T in Kelvin is the same as delta T in Celsius. Then the delta T from the water's perspective. The final temperature of the water is 32.8 degrees Celsius. The initial temperature of the water is 20 degrees Celsius. So the delta T for the water is 12.8 degrees Celsius. Okay, so now we're ready to plug these things in. I'm going to simplify even a little bit further. I'm going to say, let's solve for the Q of the water first. That's going to be 1,000 times 4.184 times 12.8. So the Q of the water is equal to 53,555 joules. So now we can take that value that we just solved for and put it in here. And then we're going to solve for the Q of the iron, really the initial temperature of the iron. So here's what it's going to look like. And again, as I've been trying to really emphasize, you need to watch your signs. So the negative MC delta T for the iron equals 53,555 joules. that negative sign that I put in right here is super, super important. The energy lost by the iron is the energy gained by the water. Okay, so now it's order of operations and solving for this. So let me give myself a little more room here. What I'm going to do is I take negative 400. I'm going to take 400 times 0.45. I'm going to distribute the negative sign to that. So you get negative 180. Grams cancels with grams, so you're left with joules per degree Celsius times 32.8 minus T initial equals 53,555 joules. I'm trying to isolate this. I know your guys' initial thought is to distribute. Resist. The math is slightly easier if you first divide both sides by joules per degree Celsius. Negative 180, I'm sorry, negative 180 joules per degree Celsius. That gets it out of the way over here. Joules cancels with joules. 1 divided by 1 divided by degree Celsius is going to be degrees Celsius. So now we simplified this a little bit. We have 32.8 minus T initial equals negative 297.53 degrees Celsius. Now what I do is I add T initial to both sides. That gets it out. That gets it out over here. And then I have a positive value over here. And then I'm going to add 297.53 degrees Celsius to both sides. That gets it out over here, and I'll be left with my answer in T initial. That's what I'm solving for. So T initial equals 32.8 plus 297.53, 330 degrees Celsius. And that makes sense. Again, I really encourage you to take a step back and actually think about your answers to see if they make sense. We heated this iron up in a flame. Of course it's going to be super, super hot. It raised the temperature of the water by 13 degrees Celsius. And remember, I told you with a specific heat capacity of 4.184 joules per gram degree Celsius, it resists temperature change. So the fact that we were able to change the temperature by 13 degrees means that whatever we put in there had to have been super, super hot. So 330 degrees Celsius makes sense. And again, the most important thing really that I need to point out is this negative sign. If you don't have that negative sign, you'll see that the answer just doesn't make any sense. The energy lost by the iron is equal but opposite in sign to the energy gained by the water. Negative Q of the iron is equal to positive Q of the water.